everyone to BRNE's Pipeline Modeling Basics webinar. Today, we'll be going through the various options for sizing pipelines, from relatively short flare header networks to cross-country oil and gas pipelines. I'm joined here today with my colleagues Omar, Ganank, and Dee. So let's start the presentation proper with answering the question, why is it important to even size the pipelines? Well, just like most engineering problems, it often boils down to a balance between CapEx and OpEx. Having an extremely oversized pipe will obviously cost more, not only because increasing the size often requires thicker pipe walls and thus more material, but also because past a certain point, logistics of transportation and installation will start to scale out of hand. On the other hand, if you have an undersized pipe, this will lead to extremely high pressure drops. And for some gas pipelines, that might even mean you will start to have choking occur, since lower pressures lead to higher volumes and higher velocities. All this means you would need to invest more into your pumps or compressors and whatnot. But of course, beyond complex multi-phase pressure drop calculations, there are also some important thermodynamic calculations required for other considerations. For example, figuring out the liquid dropout for gas pipelines especially, to ensure you're not forming any solid hydrates that might form across your whole line, and determining if insulation is required or sufficient to deal with heat loss if you're working with a colder environment. Or, of course, figuring out how much feed you can put through your pipeline before the pressure drop starts to get out of hand. ProMax can do all of these things, and we have three main tools to help you do that. We have a quick and easy line sizing analysis tool that requires minimal inputs, and that will give you valuable information in about 10 seconds. A more rigorous pipeline block that deals with heat loss calculations, phase changes, etc. We also have that available here. And finally, if you are dealing with huge pipeline networks that you draw on GIS software like Google Earth or ArcGIS, you can also import all of those drawings with its coordinates and geographic information into ProMax so that we can thermodynamically calculate its pressure drops, any liquid dropouts, etc. So let's start with the easiest tool, our line sizing analysis. This line sizing can be added to any stream, and we'll grab that stream's information like composition or any other thermodynamic information to do its multi-phase pressure drop calculations. It has two main modes. You can quickly size your pipeline by specifying an acceptable maximum pressure drop amount in terms of pressure drop per length. You will see a bit later, this is very flexible in how you specify it. And that would have the analysis tell you what's the size of pipe that will not exceed this maximum pressure drop. Alternatively, if you already have information on what line sizes you're working with, you can put those into it and we'll tell you what pressure drops you expect to see out of it. We also have some additional options below if you want to get into more detail, but worry not. A lot of these have excellent default values for you to work with. For example, you can input your pipe roughness or use a drop-down input on ProMax and select a representative material that will have a recommended pipe roughness to go along with it. If you have a non-horizontal pipe, like a vertical or angled pipe, you can also specify an angle of inclination where positive means it's tilted up and negative means it's tilted down. And finally, we have a wide array of multi-phase flow correlations to choose from. By default, you'll be seeing we use Bex and Brill since it works with any angle. But if you want one that's more specific to your specific application, you have a lot of them to choose from with their different the different ways of them being established to begin with, as well as different requirements. And in addition to rating or sizing pipelines for their specific pressure drops, this analysis also does erosional velocity and maximum allowable working pressure calculations that will throw out warnings at you if any of these rules are broken, so that you know that you're not breaking any established design limits. So let's take a look at all of this on ProMax. What I have here is model of a GSP or gas subcooled process plant. In simplified terms, it's just a demethanizer. Line sizing is especially important here because the cooling system heavily depends on pressure drops. So if you undersize your pipelines, you might experience pressure drops in locations where you don't want to see pressure drops. And you may not have enough as it goes to your cooling devices like the JT valve or the turbine. So let's do a quick one using our line sizing analysis. We'll start on stream 2, which is this one, the feed. If you double click on any stream on ProMax, you'll get this project viewer window with all its information. Since we're adding an analysis, we will go to the analysis tab over here. And we'll add in a line sizing analysis. Analyses on ProMax are just additional engineering calculations that may or may not change, require different properties from your actual stream. And in this case, we're going to use a line sizing one. Clicking OK will set up what you saw on the PowerPoint presentation. And we will just keep things simple with a 1 bar per 100 meter pressure drop. We're going to keep it at a standard pipe schedule. And that's all the information you need to run it at a basic level. I click on execute, solve, and straight away you see it recommends a 6-inch pipe that is standard pipe schedule. If you're more familiar with the metric, we also have a DN, so diameter nominal of 150. And if we look at the bottom here, we can see that the actual pressure drop is about 0.75 bars per 100 meters, which is lower than 1 bar per 100 meter. As I said, not only do we have a drop-down menu with a lot of different units for you to choose from for this, the unit for the horizontal linear pressure drop is very customizable. For example, if you have a 250 meter pipeline and you want to specify that instead, you can just change this 100 to 250 and automatically the unit conversions will occur. Bar can be replaced with PSI if you want to mix up the units, and etc., etc. And as usual, if you want to revert something back to its default units, you can just delete the unit and it'll revert it back. As you can see here, I'm sure most of you have noticed, the number over here constantly changed because the unit conversions were constantly being applied each time I make a change to the units. Okay, so this is all well and good. It's recommending me a 6-inch pipeline, but you see a little warning at the bottom over here, as well as on the project. It's a bit small on your screens, but I'll read it out. It says, warning, the value of 19.1 meters per second for mixture velocity exceeds the value of 18.8 for erosional velocity. What this means is, if you run this so fast, you run the risk of the gas being so fast that it starts to erode your inner walls of your pipeline. So what can we do about that? So obviously, we will want to work under the erosional velocity. And for that to happen, you can either select a bigger pipe, or we have an input over here called maximum velocity, where you can manually limit the velocity of your pipeline based on its design. So since our maximum velocity is about 19 meters per second, I'm going to put in a bit of a leeway and just specify 15 meters per second. I click on solve again, and sure enough, my pipe size went up from 6-inch to 8-inch. And the DN went up from 150 to 200. Obviously, my pressure drops again from 0.75 to about 0.2 bars per 100 meters. And now the warning is gone. Over here at the bottom, you can see here the warning is instead replaced with maximum velocity is exceeded for specified pressure drop. Therefore, the reported nominal size is based on the maximum velocity specification, which is what it is, 15 meters per second. That's what I'm looking for. What if this fluid was coming out directly from a well and may have some sand in it, for example? Since sand in the gas would make erosion even worse. Well, if you scroll down at the bottom here, you see under erosional velocity, we also allow an input of sand fluid mass ratio. For example, if I put in a sand fluid mass ratio of 30 ppm and solve it again, you will see we get that same error before the mixture velocity exceeds the erosional velocity. And then from there, you would work out what's the next pipe up, or you can change the maximum velocity to get that sorted out. And finally, with regards to the maximum allowable working pressures, if we were to specify a material of construction, for example, over here, if you click on that, you'll see we have a long list of different steels. We have here carbon steels, we have cast irons, cast steels, nickel alloys, etc. Most commonly for this, you'll probably use something like stainless steel. And we will just randomly select A312, which is 316 stainless steel. Click on OK, I'll assume no corrosion allowance. And when I click on solve, you'll see my maximum allowable working pressure for this particular pipeline is 92.5 bar gauge, which is perfectly fine. You see no warnings related to that because our operation pressure in this case is only 55. So that summarizes the easiest line sizing you could do with line sizing analysis. Of course, we have ProMax is all about convenience and workflow solutions. We have had clients that really liked how quick and easy this is, but wanted an easier way to apply it to every single stream. As you can see here, there's about 30 streams on this flow sheet alone. And you don't want to have to go and double click every single one and put them in manually and set them all up. So what we have developed, one of the things that we can do is use a custom report. And in this case, if you see in this Excel file, because we have very good integration with Excel, we have a custom report that looks a lot like what we see in that line sizing analysis, where you can put in all your inputs individually. Once you have set this up, you can go into your ProMax file, click on report, and use the template and generate it for all of your streams at once. So as you can see here, I am selecting all of the streams at once. They're all picked. If you click OK and navigate through a few other windows to specify what you're looking for, the end result will be something like this. You will have a Excel workbook with all of your streams included. If I look to the right, you can see there are quite a few streams included, as well as multiple flow sheets to encapsulate them. And at the bottom over here, you can see the pipe size as well as the DNs for each stream. It would be neatly organized in a table for you. So all this does is basically does the analysis on every single stream in the flow sheet that you have selected. And it's a very convenient way of organizing your information all on an Excel table. So we have options for you to do it either individually on a stream, or you can apply it to everything in your ProMax project. Let's go back to the presentation. We have talked about how to use our easiest tool, but you'll notice being simplistic comes at a cost. It ignores a few important factors. For example, ignores phase changes as the pressure drops. Sometimes you will have phase change occur. It ignores heat losses, and it mostly just models a single straight pipeline. It can be at an angle, but it's mostly just straight. So all these will not be very applicable if you're working with very long pipelines that bend and curl, or have huge pressure drops that will have huge swings in your phases. So this tool is best for shorter lines. However, even for longer pipelines, it's still useful in the sense that it can give you a good starting point. If you put it in, you will see, okay, maybe I should start with 8-inch pipe and then work on from there. But of course, if you want to model longer pipelines, you will need a more detailed analysis, and that's where our pipeline block comes in. The pipeline block will allow for many, many more inputs, as well as generate a lot more meaningful results. It does this by rigorously modeling the phases at every interval. Of course, there's a bit of hierarchy in its use. This is mainly to provide clarity in your flowsheet and properly compartmentalize your information. So at the top of the hierarchy, you have the pipeline blocks itself, each one of these green pipes. You can have as many as you want on a single flow sheet, but you need at least one per flow or compositional change. So for example, stream 15 and stream 17 in this image has two different composition of flows, so they have their own individual pipelines. And after they mix, obviously the flow and composition would change. So flow on stream 39, you expect another pipe. Within each of the pipes, we divide it up into what we call pipeline segments, and each segment is often representing either a straight pipe or some sort of fitting or nozzle, etc. So in this image in the middle here, you can see a long winding pipeline. So you would have one segment for this straight part, maybe one segment for the fitting that bends it, and another one for the straight part, and another one for the straight part, and another one here. So a long winding pipeline would be divided up into many straight pipeline segments. And of course, each segment can have as many calculation increments as you would like. You would add more calculation increments if you're looking at studying nonlinear behavior to prevent aliasing. For example, vaporization or condensation occurring in the pipe. Why is this important? Well, aliasing is a big deal for nonlinear systems. For example, here, if we sample at every one of these blue dots, we might assume the trend looks like the blue line, but in reality, it might be the red one. Who knows? So at this point, you might want to add in more calculation increments to smoothen it out. Within each pipeline block, you will see this screen under its process data. To add a segment, simply click on Add Segment at the bottom here. I'll show this to you in a bit more detail when we do the little demonstration. And just like before, a lot of this screen is what you have seen in the individual line sizing analysis. We have the pipe length, the schedule, the size, thickness, roughness, etc. Slightly different here, instead of only allowing an inclination angle, you can also specify an elevation change. But know that these two are mutually exclusive, which means that if you want to specify one, you have to delete the other one first. The main difference with the pipeline block comes in terms of inputs, comes in the segment type. Each segment doesn't have to just represent a pipe. It can also be a fitting, a reducer, or an isentropic nozzle. In the case of fittings, it will open up this section of the table where we have a large list of fittings for you to choose from that will have their own resistance coefficient or equivalent length that comes with it. Of course, if you have your own resistance coefficient or equivalent length, you can just simply put it in there for yourself and override our recommended values. Another very handy feature that comes when you use our pipeline blocks is heat transfer calculations. This will require you to add an energy stream to your pipe, as seen here, attached to the pipe. And this will allow the ProMax pipe to also account for any ambient heat loss with many different modes. You can specify stuff like the surrounding temperature. In this case, it would be if you are working with a buried pipe, it would be the surface temperature. We have a long list of iron, steels, alloys, and even some thermoplastics in terms of the materials of construction that are available. We also support a lot of different modes, such as buried, or maybe your pipeline is submerged in some fluid, or it could also be above ground. In terms of buried ones, we have a large list of ground types that will come with their own thermal conductivity values. All of this will help you calculate the overall heat transfer coefficient seen on the left here. And this will help you account for any heat losses or gains to your surroundings. Of course, once again, if you have your own numbers, you can override any of these numbers by just inputting them here. And of course, there are a few other features available, which we'll be going through, including accounting for the use of drag reducing agents, automatically calculating any freeze out, especially with hydrate formation. And we have a lot of meaningful results as well as ways to visualize them, such as seeing all the different flow regimes at every increment along your pipe to make sure you're operating at a good Reynolds number, as well as making sure that you can see your results in a neat and tidy way using our plot system. So let's take a look at all of this back on our ProMax file. What you see on your screens now is just a simple pipeline where gas 1 and gas 2 mixes, goes through pipeline 1, mixes in with gas 3, and goes through pipeline 2. Once again, if you recall the hierarchy, since a compositional or flow change occurred in mix 101, it will need its own pipeline afterwards. And you can put in as many pipelines as you want by just going to ProMax auxiliary objects on the left. And it's a simple click and drag, and you can add another pipeline. So if you want to attach this to anything else, you can do so like that. So let's take a closer look at pipeline 1. If I double click that, under process data, you see that table I showed you before. It currently has 3 segments. I'm just going to show you how to add a segment if you need that. To add a segment, you can either click on add segment at the bottom left, or if you want to insert a segment between existing ones, you can always right click on that one and then click on add segment there. But I'm mostly interested in adding it at the bottom, so I'll just click on add segment, and then a new blank row will form. There's not too much inputs required. I'm just going to assume, let's say, about 9 kilometer pipe. I'm going to follow the same pipe schedule, AT. And you can see here, you can pick lots of different pipe schedules available for you. And each of them will have their own associated nominal pipe size, either selectable in inches or in DN, if you're more familiar with that system. I'm just going to copy what we have already, an 8-inch pipe. And that's all I need. That would help me calculate my pressure drops. Of course, the main difference here now is, as you notice here, we have a fitting. And in this case, the fitting is a 45 standard elbow. If I wanted to change this, I just have to click on that little arrow And you can see a long list of fittings available for you to choose from. And this includes a few valves, half open, full open, etc., etc. Of course, if you do not, if you have your own numbers, you are free enough to just overwrite these values over here, either your equivalent length or a resistance coefficient. So this will help you calculate pressure drops just due to hydraulic effects. Of course, there is also temperature losses, especially true if you are working in a very cold country, for example, and with very long pipelines. And to account for that, of course, without an energy stream attached to it, it will assume the pipeline is adiabatic. To fix that, you just have to go to ProMax streams and drag out an energy stream and attach it to the pipeline as such. Doing so will enable our heat transfer options. As you can see here, some of them have already been previously specified. But for my latest segment that I add, segment number 4, I'm just going to say ambient temperature is -1. And if I wanted to select a different material of construction, I have the same list as you saw before, now with extra thermoplastics, if that's applicable for you. But I'm just going to copy and paste whatever is down. If you have a huge pipeline with lots and lots of segments, you can of course use our copy to bottom function over here. And it works even if you select multiple things. So I select both of these and I click on copy to bottom, it will copy both of them down. In this case, the pipeline is buried about 61 centimeters under the ground. And in this case, the ground we have selected is dry clay. But as you can see here, we have quite a few options for you to work with, including snow, etc., etc., gravel. Yep. So now that that's all set up, I can execute the flow sheet. Everything is green, and our pressure drops would all have been calculated for us. But seeing as this is a gas pipeline, one of the more important things to look at is, of course, the liquid dropout. To see this, you can just go to increments, and you can look at liquid flow. We start with 0, and then we have some amount as we moved on. Of course, this isn't very friendly to the eyes. That's why we have a plot tab over here. It's very flexible. By default, it will show you the cumulative pressure drop per length. Let's change that to instead look at liquid flow rate. From this graph, you can quickly see that we have liquid dropout occurring mostly at about the 7 kilometer mark. However, you also notice this is a bit janky in terms of what it is. So we might consider adding in some calculation increments to make sure we have the correct trend. It could very well be possible that this is nonlinear. So to do that, we go back to process data, and under options, all the way on the right, we can increase the number of length increments. I'm just going to put in an arbitrary number 10 and copy it to the bottom, and all of them are 10 now. I'll re-execute the pipeline, and now you can see a much clearer picture of when and where stuff are occurring. If you want a better resolution of what happens in this region, you can once again just increase the number of increments. So doing all of this will allow you to accurately model your pipelines, figure out pressure drops, etc. But what if you also want to look at hydrate formation? Right now, all these gases are dry, so no hydrates will form. I've remodeled the first pipeline into this flowsheet, and we can model TEG units, TEG units, dehydration units. But because we're focusing more on pipelines, I have just represented it with this simple block right here. This is a shortcut block. We will be covering how to model TEG units in a future webinar, so stay tuned for that. But as you can see from this block, all we have specified is that our outlet saturation concentration is roughly 7 pounds of water per million standard cubic feet. This is the average amount that most dehydration units target. But let's assume we have an issue with the TG unit. And now we have a lot more water entering into our pipeline. What is the consequence of that? So to do that, I'm just going to delete this and assume 100% saturation in my gas. I re-execute it. And at the bottom, straight away, you will see warnings. And the warning you see here is the important ones are the temperature of 12.4 degrees Celsius is below hydrate formation. This warning basically tells you if you run this system as it is right now, you would expect to see hydrates being formed, and that will choke up your pipeline. Where does this form? Well, you can double click into the pipe to look, but I can just read it off this address over here. Looks like pipe 1, segment 4, somewhere in that area it occurs. Let's look at some options to resolve this issue. Well, the obvious one we can see from this analysis over here if we double click on stream 2. And in this case, when we add an analysis called freeze out hydrate and H2O dew point, click on solve. And as you can see over here, our solid formation temperature, in this case hydrates, is at about 12.3 degrees Celsius. And the stream is actually at about 11. So it's quite close, but not enough. So obviously, to account for this, one of the ways you could do is to add in insulation. Obviously, this doesn't work if the pipeline is already existing. But if you were to add insulation, it will prevent this 37 degrees Celsius gas from cooling down so much to the environment. To add insulation, you can just go to the pipeline and it's as easy as clicking on insulation. Just add a layer. And in this case, I'll just say add a urethane foam layer and just put in maybe 1 cm of it, just as a random number. If I re-execute it, remember this number used to be 11. Now, thanks to the insulation, it is now closer to 14. And if we were to look at the warnings again, it does not say we're under hydrate formation. The warnings do tell us that we are awfully close to it. So that insulation sort of helps, but not really. Of course, there are many other ways of accounting for hydrates, many of which we will cover during our hydrate suppression webinar in the near future. But I'm just going to bring in one of the quick methods, which is to just add in a bit of methanol. We'll go through more in the detail during the actual webinar. But as you can see here, I've just added about 15 kilograms per hour of methanol, 100% methanol. And when I re-execute it, you'll see that all my warnings disappear. I no longer have any issues, even though my temperature dropped a little bit. If I double click on this, you'll see that my solid formation temperature dropped from about 12 down to 5 degrees Celsius. And I have a healthy distance between what I'm operating at and what the solid formation temperature is. We'll go through more on this theory, as I said, during our hydrate suppression webinar. But as you can see from here, we have a lot of different ways which you can use a model of a pipeline to look at the options when it comes to not just pressure drops, but also auxiliary stuff like insulation and hydrate suppression. We have seen how to specify pipelines individually. But what if you have a GIS or Google Earth drawing of your enormous pipeline network? That could be thousands, hundreds of thousands of nodes, which means thousands of segments. To me, that sounds like a copy and pasting nightmare. This is where our GIS comes in. It accepts information from a shapefile or Google Earth KMZ file that has all your elevations, pipe lengths, all those geographic informations, etc., including any notes that comes attached to them, names, etc. And then it grabs all of that from that shapefile or KMZ file and puts it into ProMax. Doing this allows you to apply all our thermodynamic calculations like multi-phase pressure drops, liquid holdups, and hydrate formation, etc., and apply them into your specific pipeline. So you take from a GIS drawing into a ProMax drawing with every single one of these pipelines specified. By doing this, you can find out where your bottlenecks are. You can also, if this is something you're designing, you can also take a look at seeing where would be the best place to add in a compressor station. And best of all, you can, because ProMax is also really good at a lot of gas processing modeling, you can model upstream treatment facilities or downstream treatment facilities, etc. So you can integrate everything onto one file rather than have it all separated. So let's take a look at this final feature very briefly on ProMax. But first, just to show you what a GIS drawing might look like, what you see now is Google Earth. And we have just drawn a bunch of lines to pretend like we are making a little gathering area over here, where all these blue lines merge into the green lines and then has a compressor station over here. One of the advantages why people like to plan out their pipelines using this is because if I wanted to draw a pipeline, I can easily just draw it along the line. And in doing so, I would not have to worry. I would not have to measure the lengths or elevation changes. Google Earth or whatever GIS tool you're using would have all the information pre-built in it. So designing a pipeline is as easy as just drawing it onto the diagram itself. But what does that look on ProMax? So to access our GIS tool, there's a button over here called the GIS tool under our ProMax ribbon. Clicking on that will bring up our GIS window. And you will be able to import any of your KMZ files, etc., from Google Earth or any ArcGIS. As you can see here, in the interest of time, I've pre-imported this. And if I zoom out a little bit, you will see that this thing is somewhere northwest of Houston in Texas, America. Zoom back in. You will see all the pipelines and their associated arrows pre-set up for us. If I cross that out, you will see that if I wanted to bring that into ProMax, it's as easy as doing a bit of setup over here and then clicking on Create Flowsheet on the bottom right. One interesting thing that we can also do is choose our elevation source. So if your GIS information has a bunch of elevation information, you can use that. Or if you want to use a satellite information, you can also use that instead. So you can compare the two if that matters to you. Clicking on Create Flowsheet will bring up a loading bar, which unfortunately is showing on the wrong screen at the moment. But it will essentially draw out exactly what that pipeline network would be for you. And of course, some information, oh, there it is. It's all being connected at the moment, and yeah, it's done. So as you can see here, there's a very striking resemblance to what we had in our original file. A lot of it looks the same. And all of this is automatically generated for us. So I did not have to go into each pipeline and create them on my own. For example, if I double click on this pipeline, you will see that all of this pipe lengths, as well as their individual elevation changes, are all automatically imported from the GIS tool. Of course, you would also have to specify some other things if they do not come with your GIS information. For example, you may not have your pipe size specified in Google Earth, for example, in which case you'll have to specify them. But once again, it seems a bit tedious to specify all my pipelines one by one. That's why on our GIS tool, we also have a flowsheet tool. So if I bring that up again, we have our GIS side of the tools, but we also have our flow sheeting tools. And as you can see here, I can quite easily specify, for example, a 3-inch pipe. and then click on copy to bottom. And that will automatically populate every single pipeline on that flow sheet with a 3-inch nominal pipe size. Of course, there's a lot of pipes to go through, so it might take a few seconds, but generally it's a very fast process, very convenient. And if I go back to my flow sheet, I double click on this, you can see 3-inch is automatically populated here. If I click on another random pipe, you see 3-inch is automatically populated here as well. This is also very useful if you want to specify other things, for example, your pipe schedule, any heat transfer information, like maybe everything has the same ambient temperature, ground type, varied depth, etc. And of course, any of the options you prefer, like if you want to change your multi-phase flow correlations, etc., etc. Okay, so after all this is said and done, of course, we need to specify a bit of the inputs here and there. And we go through a bit of setup, which gets a lot easier in our next release when we have our simultaneous solver. But the end result would be a fully converged flow sheet, as you can see here, where you can see if I needed at least 19 bar gauge at the end, what do all the other pressures have to be? It also answers very important questions like, will there be any hydrate formation? Will there be any liquid dropout? And would there be any issues here and there, etc. And liquid holdup would also be reported on every single one of these pipelines, which means that you can see where your liquid is more likely to gather in. Of course, this is a very basic webinar, so we won't be going in too much detail. But if this is something you're interested in and you have a shapefile you would like to see on ProMax, please just reach out to us. Our support for our clients is 100% free, and we will set this up for you, no problem. And that concludes our short demonstration on basic pipeline modeling on ProMax for today. So once again, I would like to thank all of you for taking the time out of your day to join us.